Hey everybody, welcome to week 2 of PS 398. So the topic of today's lecture is rationality. So you've been promised a class in rationalist international relations, which is in some sense methodological and substantive stand-in for game theoretic or strategic or however you want to call it. It's important to recognize that rationality is a fable unto itself. So in the previous lecture, I characterized what we do in the mathematical modeling in the social sciences. I characterized it as something akin to writing fables. This isn't my idea. This comes from a well-known economist named Ariel Rubinstein, who is a famous game theorist. We'll be looking at some of his models later on in the class. He has a wonderful book, and actually it's available for free on his website. So actually I should just sort of put the website here. So he has free. All of his books on his website are free, and one of them is entitled Economic Fables, and it's actually a really interesting read, and you might want to give it a look. You might wait until after this class so that you have a better sense about what the fables look like before you start talking about what is the nature of fables. It's a fun thing to think about. You know, what is this act of social science, or this one small part of social science? What actually constitutes that act? So we have fables. We're going to be talking about fables in this class. Underneath all of the fables that we'll be talking about, fables of reputation, fables of best response, fables of equilibrium, fables that tell us what is the state and what does it do, fables of the bargaining model of war, all sorts of fables, right? Underneath all of these fables is a foundational fable, the fable of rationality. And it's so rationality, it's played an interesting role in international relations theory. It's actually worth talking about a little bit about before we get into what the fables are today. So in international relations, rationality plays a really important role in some theories. It plays a really unimportant role in other theories, and some theories outright reject the idea of rationality. Let's take a visit to the bookshelf of awesomeness. Let's put on some bookshelf of awesomeness music. Oh, it's always good to go to the bookshelf. So let's think about two important books in the international relations theory tradition. So Kenneth Waltz's Theory of International Politics. This is from 1979. This is the Bible of neorealism. And Bruce Bueno de Mesquita's War Trap. This is a beautiful book by Bruce Bueno de Mesquita. This is from 1982. I think it's 1982. 1981, geez. So, both of these books, one you may have guessed from the title, but both of these books provide a theory of international politics. They both involve some interesting passages about the role of behavioral assumptions in such theories. They're not unique in that, but I think that what gets mentioned here is especially useful. So, let's start with Neorealism, 1979, Ken Waltz. I'm reading from page 91 in the chapter entitled Political Structures. Oh, this stuff is also good. In a micro-theory, whether of international politics or of economics, the motivation of the actors is assumed rather than realistically described. I assume that states seek to ensure their survival. The assumption is a radical simplification made for the sake of constructing a theory. The question to ask of the assumption, as ever, is not whether it is true, but whether it is the most sensible and useful one that can be made. Most sensible and useful. It might be a little bit of a cute idea to think that those things go together all the time, but let's keep going. Far be it from me to tell Ken Waltz what to think about these things. Whether it is a useful assumption depends on whether a theory based on the assumption can be contrived, a theory from which important consequences not otherwise obvious can be inferred. Whether it is a sensible assumption can be directly discussed. So basically, Waltz says, I'm going to try to simplify how I think states behave. In a lot of international relations, the unit of analysis is just the state, which makes sense. However, we'll see next week that this introduces some difficult nuances. You'll see what I mean next week. And so he's trying to construct a theory about how states interact with one another. And in order to do so, he assumes that states want to survive. So Waltz himself is not a rationalist, and he would take great pains to make sure that people didn't paint him as a rationalist. There are actually some papers on the topic of whether Ken Waltz believed in rationality or not. I'll put a citation on the screen. But regardless, he's providing some animation, and he's telling us that when you construct a theory of international politics, then you have to impose some behavioral assumptions, right? So that's sentence one, right? The motivation of the actors is assumed rather than realistically described. So we're not going to try to figure out what the causes of the motivations are. We're going to take the motivations as given, and then we'll construct a theory about how people will interact given those motivations. So that's Waltz. By the way, I wish we could just do a book club on top of all this other stuff that I'm throwing at you. If you haven't read The Theory of International Politics, which is a pretty big if, this is something that a lot of IR students read in grad school, not in undergrad. But if you can find a cheap copy of this somewhere, even just the first few chapters will change how you think about international politics. Even before you get to Waltz's theory, Waltz's chapters about what theories are and what they do, that'll change your life. Okay, maybe that's a little bit strong, but it'll change how you view IR theory. That seems much more limited. It will do something in between change how you view IR theory and change your life. Book 1. Book 2, The War Trap by Bruce Bueno de Mesquita. Bueno de Mesquita is a much more committed rationalist than is Waltz. Waltz tries to tell people that he's not a rationalist, even though he says that states engage in self-help behavior in order to survive. Bueno de Mesquita is much more actively a rationalist. He wants to use states as the unit of analysis, but he also knows that there are some serious nuances in how to think about state preferences, like we'll be discussing next week. He's going to speak in terms of a leader who has policy preferences. When he says leader here, he means the leader who can be thought of as the stand-in for a state. On page 29, in his section entitled The Rationality Assumption, the strong leader, as I have noted, cannot afford to ignore the interests and desires of those whose support helps keep him in power, yet neither is he an unthinking tool of their interests. The key leader must make sense of the competing, sometimes inconsistent demands placed on him so that he can formulate a policy that accords with his own interests. When he does so, I assume, the leader is guided by a desire to maximize the net benefits he expects from his foreign policy choices. A policymaker will never choose an action that is expected to produce less value or utility than some alternative policy. In other words, the leader is assumed to be a rational utilitarian, interested in maximizing his own welfare. His welfare, in turn, is assumed to be intimately tied to the overall costs and benefits imposed on the society by his foreign policy. So in other words, the incentive structure of how the domestic institutions are designed, they're designed in such a way that the leader's interests are the state's interests. The key leader would not, therefore, start a war or continue to fight in a war if he perceived the net expected result to be less than that of remaining at peace or surrendering to the adversary. So in other words, Bueno de Mesquita is saying leaders, the individuals that run countries, have preferences, but those preferences are intimately tied to what goes well for the state. So in any well-designed institution, you'd like to think that whoever is making the most important decisions has interests that are aligned with the overall organization's interests, right? So you would hope that the leader of a country, you want to design institutions that incentivize that leader doing what most people would want them to do. You want the organizational structure of a company to be such that the CEO has the incentive to do not what is best for the CEO, but what is best for the company. If you design the institutions well, then those are the same thing. So the idea here is that rationality is going to be a very common behavioral assumption for us to bake into our theories of international relations. That can be formal, like in Bueno de Mesquita, or it can be informal, like in, well, Waltz, who wants to tell you he's not a rationalist. But if you read other realist thinkers, like maybe John Mearsheimer, then you would see rationality more explicitly embraced. So rationality is the foundational fable of an awful lot of fables of international politics. In other words, rationality is the underlying assumption for many theories of international politics. So as such, I think it's worth spending a week on this foundational fable. And we're actually going to look at 3 different flavors of the foundational fable. Isn't it cool that the same foundational fable can manifest itself in at least 3 ways? And by manifest, I mean mathematical crystallizations right? I mean, we're going to see 3 different mathematical angles of the same idea. Whoa, that's cool, right? That's what I hope to show you today, are just 3 equivalent fables, one of which we're going to proceed with for the rest of the class, but 2 of which are important to remember substantively, so that anytime you see the one fable that we'll use, the fable of utility maximization, you'll also know that underneath that lives 2 other fables that have slightly less laughable stories. So in the A block, I want to show you the most balanced, I would say, sort of the middle option in terms of the difficulty and the substantive pleasantness. Is pleasantness a word? Substantive pleasantry, pleasant ability, pleasantness, pleasantitude, pleasantness. So the first fable in the A block will be somewhere in the middle in terms of how technically difficult is it and how substantively pleasant is it. That fable is the fable of the rational binary preference relation. What, you're like, I heard that one when I was 5. That was my bedtime story when I was a kid. That's just going to be, as you might have guessed from the name, it's going to be all about binary comparisons between alternatives. The second fable is the most commonly used fable, so it's the technically easiest to use and the substantively most impoverished. So in the B block, we'll be talking about the fable of the utility maximizer. And so this fable, the utility maximization fable, which Bayon de Mesquita just referenced explicitly, that fable is the easiest to use in a technical sense, and so it's what you'll see in most papers in international relations or in other disciplines. But it's also substantively the weakest. The story that it tells is highly implausible, and so it's actually the version of the story that you hear the most whenever you hear uncharitable caricatures of what rational choice theory is and what it purports to do. Now the third fable, which we'll be talking about in the C block, the fable of rational choice, that's the hardest to use. It is the easiest to verify empirically, and it probably gives not the richest story because a lot of its strength lies in the fact that it isn't trying to tell a story, but the story that we're going to be able to back out from it is probably the most satisfying from a substantive standpoint, but it's going to be a real pain in the butt to use. And so part of what I'm going to try to do is show you all 3 fables, but along the way, I also hope that you'll pay special attention to the connections between the fables. So that's our goal. We want to talk about this foundational fable of rationality. We want to know what is the motivation for the fake people that are going to live in our fake fable worlds. Let's get started. We always take books back to the bookshelf of awesomeness, or else, I think most of you haven't taken a class with me before. If you've ever been to my real office in David Kinley Hall, there's usually just like big stacks of books because I'm always just wanting to go get a book and then I read the book and then I put it down. And I kind of I'm like The Sims. You ever play The Sims? This is what old people do, is they play The Sims. So you go, you get a book, and you put it down. And you go and you get another book, and you put it down. And next thing you know, there's a stack of books. And that's my office at David Kinley Hall, which I miss terribly. I hope you guys are doing well. I don't know how you're feeling in your dorm rooms or in your apartments or wherever you've chosen to spend this semester. But regardless, I hope you're doing well, and I hope that the adjustment hasn't been too tough. So here in the A block, we're going to be talking about the fable of the rational binary preference relation. Yay! I mean, I know that's the fable that you've been dreaming of hearing. That's whenever I was a kid, I would jump onto my grandparents' lap and say, "Oh, tell me a story about rational preference relations." And they didn't know anything about that, so they were like, "What's wrong with this kid?" So the basic idea in all 3 of the models that we'll be discussing, the most foundational aspect of it is the fact that we have a set of alternatives. And I'm going to call that capital X throughout today's lecture. Whenever I say capital X, I mean the set of all alternatives or outcomes. So in classic decision theory, which is what we're talking about today, the alternative that you choose, it's assumed that you have agency. If I choose an iced latte out of all the options available to me at Starbucks, then I get that. The Urbana Starbucks is fantastic, so it actually is true that whenever I order a venti iced latte, I get a venti iced latte. Other Starbucks, less so. So here the basic idea is that you're choosing among alternatives. We're then going to apply that logic in game theoretic contexts where what you choose isn't sufficient to know what the outcome will be. The idea of game theory is that the outcome depends not just on your choices, but on other people's choices too. It'll generalize just fine. So today we'll be talking about what it is to choose from things over which you have perfect agency. And then we'll move on to more advanced contexts in future weeks. To keep life simple today, and you're like, this doesn't feel simple whatsoever, but to keep life simpler than it would have been, we're going to assume that X is a finite set. If you were so inclined, you could enrich this theory to allow for larger sets of alternatives, infinite alternatives, uncountably infinite alternatives, sort of like a whole real line or something like that. But for the basic points that I want to make, the substantive points that you need to be shown to know what rationalism is from all three mathematical angles, it will be more than enough for us to have a finite set of alternatives. So capital X is finite, and throughout I'll be choosing arbitrary letters for alternatives like A, B, C, or X, Y, Z. A is an element of X, B is an element of X, and so on. So that's just a way of saying that something is an alternative, something that the decision maker, so we have a decision maker that's going to evaluate these alternatives, and everything that lives in the set of alternatives is something that the decision maker is evaluating. What's nice about the fable of the rational binary preference relation is that what happens in the story is incredibly straightforward, and we don't need anything other than a ranking on X. So when I say a ranking on X, what do I mean? Well, I'm going to introduce the idea of a preference relation through this squiggly greater than or equal to sign. So that sign is read, is at least as good as. I'll repeat that. This squiggly greater than or equal to sign is read, is at least as good as. Now let's think about what somebody might say that about. Is at least as good as is not a complete statement, right? So it doesn't have a subject, and it doesn't have, is that a direct object? Is at least as good as. It's the object, I think it's just the object of a preposition. But it doesn't have any nouns in it, right? It doesn't have any nouns. We need nouns. So what are the nouns that go in between? We need noun is at least as good as noun, right? Okay, well let's say that iced latte is at least as good as water, or is at least as good as coffee from this morning that I haven't put the mug away yet, or whatever, right? So whenever I say is at least as good as, clearly I'm talking about two alternatives, right? Not zero, not one, not three, two alternatives. Not quite. So I'm allowed to talk about an alternative twice. So I might say that water is at least as good as water, or latte is at least as good as latte. And you're like, what does that mean? I don't know what that means. Well, this is actually going to be pretty important, so let's spend a second on it. I'll be right back. So remember, we said that when I define a set, X, whenever I define any set, that set is invariant to changing the order of the elements, and it's also invariant to repeating an element multiple times. So I can take two elements out of my set of alternatives X and have a well-formed sentence that Diet Coke is at least as good as Diet Coke. I should probably, there we go. I think it's very hard, and I have a lazy eye, and so it's hard for me to know. So I can say Diet Coke is at least as good as iced latte. That's an option. I can also say Diet Coke is at least as Diet Coke. That's an option too. Okay, let me put these back before I drink them. I'm not sure if you noticed, but I'm already plenty caffeinated. Okay, so we have a set of alternatives and a binary relation. This is called a binary relation. Why is it called a binary relation? Because it relates two things, two of the alternatives in our set of alternatives. So if I write, just for example, in an abstract sense, X squiggly greater than or equal to Y, that reads X is at least as good as Y. It looks like greater than or equal to, and it kind of serves the same purpose. If you think about two numbers, there's a relation called is greater than or equal to, which means is at least as big as, right? So if I say that 4 is at least as big as 3, 4 is greater than 3, that's a true. 4 is at least as big as 4, 4 is greater than or equal to 4, that's also a true. So this serves the same purpose as greater than or equal to. And so consequently, sometimes we refer to it as the weak preference relation. Boy, I hit that K hard. The weak preference relation. Oh man, I'm going to be an ASM artist one day. Actually, just a second. First of all, Chewy has decided to make another cameo, as he is wont to do. And second of all, your video just finished uploading from last week. So these videos, I'm filming on the weekend. I'm filming like Saturday and Sunday. And then it takes about 3 days to edit one of the movies. And you're like, oh, I'm doing math, and that's like 8 or 9 days a week. Correct answer. You're very good at math. I'm not very good at life choices. Let's see, you guys deserve some good timestamps. Let me make sure that this isn't awful. I mean, it's probably awful, right? Oh, it looks awful, but that's okay. I mean, there's only so much you're going to be able to do with this when you got this to work with, right? Nice. And I go to Piazza, which you should do frequently. You know an old person when they have to announce what they're doing on the computer as they're doing it. File, preferences, save as. That's my parents. And guess what, guys? You guys have a video now. They tell me that you're supposed to put like a fancy thumbnail in, you know, but I'm not sure if you noticed, this is all unlisted. I'm not doing this to get famous, which is good because I'm not going to turn famous, but still, you know, when you try to learn how to make a YouTube video, oh, I was doing the numbers, right? Greater than or equal to, etc., etc. So that's what we're saying here is that the decision maker, so when you order the numbers, right, so it can't be the case that 4 is bigger than 3 for you and 3 is bigger than 4 for me, right? So when we get taught greater than or equal to, equal, and less than or equal to, that's just a property of the numbers that actually it's axiomatic. This is how you construct the numbers. The idea here, however, is that given a set of alternatives, iced latte, Diet Coke, water, given that set of alternatives, our decision maker is allowed to come up with whatever ranking that they want, and we're going to capture that ranking through this binary preference relation. And so if you really want to highlight the fact that this is an individualized thing, you can put a little subscript I to let us know that decision maker I, that's his name today, or her name today, or their name today, or Chewy's name today. So the decision maker's name today is I. And so that's just our way of remembering, in case we need to, that everybody has their own individual preference rankings. So we're going to assume that our decision maker is equipped with not just a binary preference relation that is read is at least as good as, but also that binary preference relation satisfies certain properties. What does that mean? It means that we want them to be rational, and the question is, what sort of assumptions about a binary preference relation are going to be required to get something that looks like rationality? And it turns out that the fable of the rational binary preference relation is going to require 3 properties of this squiggly greater than or equal to sign. It's going to have to satisfy 3 properties, which we'll be able to state precisely. And those 3 properties combined together are going to be what rationality looks like within this particular fable. So it's going to be easier to introduce the first 2 of these postulates, these positive behaviors, these assumptions about motivations, not about what the motivations are, but about the consistency of the motivations. Rationality in this world is about consistency, not about reasonableness. I'll show you some examples of that when we get to it. So let's just suppose that we have x equals ABC. There's just 3 alternatives. You're choosing between water, Diet Coke, and an iced latte. And it'll be easier in this very simple context to show you some of these things graphically. So let's just draw 3 dots, A, B, and C. And if I wanted to show that one alternative is at least as good as another, then I'll draw an arrow that starts at the first alternative and ends at the second. So for example, if I draw an arrow that from A to B, that means A is at least as good as B. And if I draw an arrow back from B to A, that means that B is at least as good as A. Okay, so these arrows are just going to be our way of depicting relationships between the different alternatives. Why don't you give that a try with greater than or equal to with the numbers 1, 2, and 3. Okay, so the first assumption that we make about our rational binary preference relation decision maker is that their preferences have a property called reflexiveness. So formally speaking, a binary preference relation is reflexive if for every alternative, each alternative is at least as good as itself. In the picture, that means that there's an arrow that starts and ends at A, these little swirly arrows. There's an arrow that starts and ends at B, and there's an arrow that starts and ends at C. So when I say reflexive, I mean all alternatives have to have one of these swirly arrows. If I got rid of the one on C, this isn't reflexive anymore. Okay, so if I add it back, now it's reflexive again. Reflexiveness is just a bit of a simple check to make sure that what we're trying to encode in terms of a binary preference relation is sensible in terms of how each alternative is compared to itself, right? So it has to be the case that iced latte is at least as good as iced latte. Well, not only is iced latte at least as good as iced latte is as good as iced latte because iced latte is iced latte. These writers are idiots. So reflexiveness, that's not especially controversial. Think about what it would mean if your preferences weren't reflexive. That would mean that for you, iced latte isn't as good as iced latte. Is iced latte better than iced latte? Like strictly better than iced latte? Well, no. Is it strictly worse? Are you apathetic between iced latte and iced latte? No. Iced latte is as good as iced latte because iced latte is iced latte. So that's not a good band name. Iced latte is not a good band name. But it would be interesting to know what band would be the band that released a record entitled Iced Latte is Iced Latte. So I don't want to spend too much time on reflexiveness because it's both straightforward and not controversial. And we're increasing in terms of how tricky they are and how controversial they are. So that one is neither tricky nor controversial. Well, let me introduce the second postulate of rational preference relations. So our second requirement is that the preference relation is going to be complete. It satisfies the property of completeness. Formally, that means that for any two alternatives, let's call them A and B. So completeness means formally that for any two alternatives, call them A and B, A is at least as good as B, or B is at least as good as A. Inclusive or, which means or both is allowed. So just to repeat, a binary preference relation is complete if for every pair of alternatives, either A is at least as good as B is at least as good as A, or both. So a complete preference relation in terms of our picture, that means that there can't be any gaps between dots. If you show me two dots, there has to be at least one arrow between them. There can be two, but there can't be zero, okay? So for example, hypothetically, maybe we have A is at least as good as B is at least as good as C, and A is at least as good as C. So this is now a complete preference relation, right? Why is it complete? Because I can't find a pair of alternatives where there isn't at least one arrow. Let's count all the pairs. There's the AB pair, we have an arrow. There's the AC pair, we have an arrow. There's the BC pair, we have an arrow. Again, just to reinforce this, we are allowed to have two arrows. So it could be that there's an arrow that goes back between B and A. So now we've got four arrows in three gaps. And that's not including the sort of invisible gaps between A, B and B, C and C, which reflexiveness has already handled for us. So this is what a complete preference relation looks like visually, and you've seen the mathematical definition, but what does it mean substantively? Well, this one is a little bit more controversial, because it means that for every pair of alternatives, you have to have at least a middling opinion about which one is better. So you'll see in a few minutes that we are going to define a concept called indifference of two alternatives. A decision maker will be indifferent between two alternatives if each is at least as good as the other. So we'll say that a decision maker is indifferent between A and B if and only if A is at least as good as B and B is at least as good as C. So that's what we're going to call indifference. But a lack of an arrow isn't the same as indifference, right? So oftentimes, decision makers aren't indifferent about their preferences on two alternatives. They actually just don't know. So for example, suppose that I asked you if you would rather have an ice-cold flabba jabba or a nice warm mug of tungstolatin. Those are fake words. These don't exist. Those are not real things. And so if I said to you, would you rather have flabba jabba or tungstolatin? There's no way that you would say that you were even indifferent. You'd be like, I don't know. Would you please tell me what the heck those are? Also, go away, you creep. So flabba-jabba and tungstolatin, they're in the set of alternatives, and by virtue of being in the set of alternatives, a complete preference relation says you gotta at least be indifferent. You either have to like one strictly more than the other, or you have to be indifferent between the two. You can't be apathetic. You can't not care. You can't say, I don't know. This is actually a pretty big deal. So as you may have noticed, this is a presidential election year. They tell me that on the news now and again. So a lot of people are going to go vote. And many of them are going to go vote for the first time since they voted 4 years ago. Many people just go vote in presidential elections. But then when you go vote, okay, at the top is the president question. Who are you going to vote for president? And most people that go to vote for president have some preference between the alternatives. And then you maybe, okay, so every election you have to vote for your representative too, right? So you go and you check one of the boxes for the House of Representatives. And maybe it's a Senate election year too, so you vote for one of the senators. And again, most people have well-formed preferences on how they feel about those things by the time they go vote. Many people have well-formed preferences before they even thought about it, but that's a different story. Then you keep going down the ballot. You went president, House, Senate, maybe there was some referenda, maybe there was a local judge or something, and then you get to executive associate dog catcher. What I'm saying here is not to demean the importance of executive associate dog catchers. Executive associate dog catchers perform a very important function in our world and are worthy of respect. That said, most people, when they go vote for executive associate dog catcher, in the event that they ever had to vote for executive associate dog catcher, most people wouldn't have a very well-formed preference on that, right? I could say, would you rather vote for candidate X for executive associate dog catcher, who is a member of the Flabba-Jabba party, or candidate Y for executive associate dog catcher, who is a part of the Tunguo-Lawton party? I had to go check those because despite the fact that Lewis Carroll has the same last name as me, I can't keep track of my nonsense words. You don't have anything to go on there. You can make a choice, and you should make. I'm not telling you not to make a choice. If you want to vote, whatever. But like, you don't know. You don't know. It's okay. That just means that rationality isn't always a very reasonable behavior to hypothesize, right? So Bruce Beyond the Mosquito was writing about leaders who are contemplating big decisions on the international scale. We're talking about somebody voting for executive associate dog catcher. Those are different things, and so it's natural to say, let's impose different behavioral assumptions. So completeness isn't always a reasonable assumption, but for many, if not most, applications in international relations, it's reasonable. And whether it's reasonable or not is a good thing to fight about, right? So if somebody said to you, I think I have an interesting rationalist theory of international relations, you might say to yourself, well, how plausible is it that this set of alternatives that's being studied is one where a decision maker could plausibly have a complete preference relation? It's worth noting that you can design a rational choice theory without completeness. It's just a real pain in the butt. So completeness is there more for convenience and for ease of analysis than it is. It's not a major substantive commitment. So again, you lose a lot of information without completeness, and so the functions that you use are way harder to work with. However, this is not where we're hanging our hat substantively. This is just one of the easy assumptions that we're trying to make. So I think what I'm trying to say is that whether completeness is a reasonable assumption depends quite a bit on how X has been specified. So if Flabba-Jabba and Tunguo-Lawton happen to be in the set of alternatives, completeness probably isn't a reasonable thing to expect. But who chose the set of alternatives? The analyst did. The writer of the fable, the architect of the world, chose. They're the one that decided what was an X. And so part of, it's reasonable to impose completeness if you were careful about what alternatives you put into X. And it's not reasonable to assume completeness if you weren't so careful about what you put into X. So that's completeness. Now we have two of our three assumptions. We have reflexiveness, so every alternative is at least as good as itself. We have completeness for any pair of alternatives. Either one is at least as good as the other, vice versa, or both. And now we need to really, those were both made mostly for convenience sake. Well, reflexiveness was more of just a, does this make any sense? Completeness is for convenience sake, and now it's come time for us to really stake our substantive claim. What is the main substantive assumption of rationality? And that's transitivity. Our third axiom is transitivity. So I'm actually going to state the formal definition first because it'll give us a chance to reinforce what if-then looks like and what it does. So we say that a binary preference relation, squiggly greater than or equal to sign, is transitive if every time that you have A is at least as good as B and B is at least as good as C. So for any arbitrary alternatives, A, B, and C in X, so for any triad of alternatives where A is at least as good as B and B is at least as good as C, right? So if you have a little chain going there, you also have to be able to infer that A is at least as good as C. So this is what I mean when I say rationality is about consistent choices rather than reasonable choices. So this is about consistent choices. If you tell me that Coke is at least as good as Pepsi, and Pepsi is at least as good as Sprite, then you also have to tell me that Coke is at least as good as Sprite. Think about what a violation of that would look like. It would mean that you like Coke at least as much as Pepsi, and you like Pepsi at least as much as Sprite, but by completeness, you like Sprite strictly more than Coke. That's a cycle. That's most people, if you told them that their preferences had a cycle like that in it, would try to correct themselves, even if you didn't say to them, oh, and that's bad. They would just say, oh, that doesn't make any sense. I should try that again. So what does that look like in terms of our picture? So let's start a picture from scratch. So let's suppose that we have 3 dots, and let's call them X, Y, and Z, just to make sure that you don't confuse them with the A, B, and C we just mentioned in the definitions. We've got X, Y, and Z. And because our preference relation is going to be reflexive, we can go ahead and draw swirly self-arrows. Swirly self-arrows is a pretty good band name, or just the swirly arrows. The arrowy swirls, less so. So by completeness, we have to fill in some of these blanks. And transitivity is going to be a way to say, well, you have to follow certain rules when you fill in the blanks. So for example, let's just say arbitrarily that I like X, that X is at least as good as Y. So I draw an arrow from X to Y. Okay. And let's say also that Y is at least as good as Z. So I draw an arrow from Y to Z. Now, transitivity tells me that because I have this chain that goes from X to Y and Y to Z, I also have to be able to fill in that arrow from X to Z, and it's got to go from X to Z. Okay? Transitivity says it all has to go downhill. All right, this is making some sense here. What would a violation look like? Well, a violation would look like X is at least as good as Y. Y is at least as good as Z. Nothing there would be a violation. That would be a violation of completeness. So if I wanted to maintain completeness, but I wanted to violate transitivity, I would put an arrow from Z to X. And then, right, you see the cycle. X to Y, Y to Z, Z to X. We're going to talk about cycles in excruciating detail next week. Cycles like these are exactly what rationality, as posited by the fable of the rational binary preference relation, is trying to assume away. And just think about what would happen if society made its choices this way, which it probably does. It would be like, oh, we choose one thing that we like more, so maybe you choose one policy that you like more than the status quo, and then you choose another policy that you like more than the first policy, and then after a couple of different policies, you say, man, I kind of missed the status quo. Right? So like on Monday, you have one policy. On Tuesday, you have another policy that you liked more than the Monday policy. On Wednesday, you have a new policy that you liked more than the Tuesday policy. On Thursday, you have a new policy that you liked more than the Wednesday policy. On Friday, you have a new policy that you liked more than the Thursday policy. On Saturday, you have a new policy that you liked more than the Friday policy. On Sunday, you have a new policy that you liked more than the Saturday policy. And then you wake up and you say, man, I miss Monday. That happens. That happens all the time. where just imagine that Monday, Tuesday, Wednesday, Thursday, make them a month, make them a year, make them a decade. So cycles happen. They happen at the societal level. They sometimes happen at the individual level. But when we talk about a rational decision maker, they're somebody whose picture never looks like this. They're somebody whose picture always has all of the arrows going the same downhill. So this is our crystallization. This is our first encoding of rationality. This is what the myth of the rational preference relation looks like. And I want to show you ways that we extend the model. So we've defined rationality in this fable with respect to the weak preference relation is at least as good as. And then it's natural to say, well, I like some things more strongly than is at least as good as. So for example, if you're offering me beverages, I prefer an iced latte to spoiled milk. Right? That isn't iced latte. It isn't just the case that iced latte is at least as good as spoiled milk. Iced latte is strictly better than spoiled milk. And I want to be able to write that. I want to have a symbol for that. Okay, well, as you may have expected, given that this all looks like greater than or equal to, if I write for any two alternatives, x is strictly better than y, x is strictly preferred to y with this squiggly greater than sign. So if I write x is strictly preferred to y, or x is strictly better than y for our decision maker, I'm going to use these symbols. This statement will be true if and only if two other statements are true. It needs to be the case that x is at least as good as y, right? So that makes sense. If 4 is strictly greater than 3, then it must also be true that 4 is greater than or equal to 3, right? Likewise here. So in order to be strictly better than something, you have to at least be weakly better than it. And, as you may have expected, it can't be the case that y is at least as good as x. So I can either put it's not the case that y is at least as good as x, or I can just put a slash through that. I can just write, or y is not at least as good as x. So in terms of dots and arrows, right, if I have just an arrow from x to y and no arrow back from y to x, then that's strict preference, right? Now that doesn't capture intensity. It isn't just, so iced latte, it isn't just strictly better than spoiled milk. It's way better than spoiled milk. But here we're thinking only about the rankings, which is to say that a binary preference relation contains only ordinal information. It contains only rankings. It doesn't tell you if you like one thing way more than another or only a little bit more than another. You either like it more or you don't. So that's strict preference. X is strictly better than y if x is at least as good as y, and y isn't at least as good as x. Well, we need an equality, right? So we have greater than or equal to, we have greater than, now we need an equal to. Well, we'll say x is indifferent to y. That's a little bit of awkward language there, so we're gonna say the decision maker is indifferent between x and y, or x is as good as y. That will be true if and only if x is at least as good as y, and y is at least as good as x. Okay, so that all kind of makes sense, right? Especially if you compare it to greater than or equal to, greater than, and equal to, this makes quite a bit of sense. What we're essentially trying to say here is that a decision maker is rational if their preferences are consistent enough that they're kind of like how greater than or equal to works on the real numbers. Now, what's interesting is the three assumptions that we made about weak preferences. We assumed they were reflexive, we assumed that they were complete, and we assumed that they were transitive. These have implications for what you can expect from these two descendant relations of strict preference and indifference. So for example, on your problem set, you're going to show that the fact that weak preference is reflexive, complete, and transitive implies that indifference is also transitive. What does that mean, indifference is transitive? Well, indifference is transitive means that if A is as good as B, and B is as good as C, if you're indifferent between A and B, and you're indifferent between B and C, then you also have to be indifferent if, then you must be indifferent between A and C. Well, that makes sense. Sort of. So actually, this is a major source of controversy in rational choice theory. this implication, the fact that the indifference relation is transitive, that's an implication. We have to accept that because it follows directly, as you'll show in your problem set, or you'll try to show in your problem set. It follows directly from the fact that the weak preference relation is at least as good as is reflexive, complete, and transitive. So we have to be okay with this because we have generated another result from our initial bedrock rationality assumption. Well, is this an okay implication? In a sense, yes, and in a sense, no. So there's a very famous issue called the cup of coffee problem. So I don't have any coffee fresh, but I'm going to go get a coffee mug anyway, just to help with the idea. Don't try this at home. This is PhD level stuff that you're about to see. So I have here 2 cups of water, and we're going to pretend that these are coffee. Okay? And I have a salt well. Uh-oh. So, here's the cup of coffee problem. So I'm going to take 1 cup of water, and I'm not going to put any salt into it. And just to highlight the fact that this is with 0 grains of salt, I'm going to call this C sub 0. Sub 0. Dun 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 dun. Woo! Don't you miss football? I miss football. Being without Big Ten football is gonna stink. I have no thoughts on whether it was the right or not. I'm just saying it's sad no matter what, right? So this is C0. And I'm gonna take this cup and I'm gonna add 1 pinch of salt. And the idea here is that I'm going to add, I don't want to do this forever, but I'm going to add a pinch that's small enough that I'm not going to be able to tell the difference. Okay, so, and just to highlight that this is a cup with 1, it's going to be C sub 1. God, I really hope that this is the computer-generated thumbnail from the YouTube video. So now I've got 2 mugs. I've got C0 and C1. This one has 0 pinches of salt, and this one has 1 small pinch of salt in it. And I'm going to issue a binary comparison between the 2. First, I taste C0. C1. That pinch was small enough that I could not detect it. So, I'm going to say C0 indifferent to C1. Because it's true. I mean, if you handed me this mug of water and this mug of water and I didn't know how these happen to get the way that they are, then, right? Okay, so now I'm going to take C1. I'm going to keep C1 as it sits. C0 is going to become C2. That means that I have to add 2 pinches, right? So I had 0 now. Now there's 1. And there's 2. This is highly scientific, right? So now I have 2 mugs of coffee again. I have C1 and C2. So I'm gonna conduct a binary comparison between C1 and C2. The best part of waking up is C2 in your cup. Can't tell the difference between the 2. So C1 is indifferent to C2. Okay, I'm going to keep C2. I'm going to turn C1 into C3. To do that, I need to add 2 more pinches. And stir. No, I want a yellow one. I want a pretty yellow one. So this is now C sub 3. So now I've got 2 mugs of coffee. I've got C2 and C3. And I'm going to conduct a highly scientific comparison of the 2. I can't tell the difference. C2 is indifferent to C3. Keep C3, and I'm going to turn C2 into C4. And to do that, I need to add 2 pinches of salt. And stir. So now I've got 2 things to compare. I've got C3 and C4. Okay. I can't tell the difference between the 2. So C3 is indifferent to C4. I can tell that there's salt in this water now. I can tell both C3 and C4 taste a little salty to me, but I can't tell which. If there's a difference in how salty they are, I can't tell. My burps can tell though. So I'm gonna keep C4, and I'm gonna turn C3 into C5. I'm gonna do that by adding 2 pinches of salt. And stirring. These get yellow. So now I've got C5. So now I have two mugs to compare, C4 and C5. Okay. Rigorous time. It's getting salty. Yup, it's getting salty. They're the same. I can't tell the difference. C4 is indifferent to C5. Now, by transitivity, the transitivity of the indifference relation, which is an implication of the rationality of the weak preference relation, the transitivity of this indifference relation has to be upheld. It's a consequence. This is something that must be true if rationality holds on the weak preferences. And what it requires is now, if I iterate the transitivity, I can infer that I need C0 to be indifferent to C5. So right? So here's water with no salt in it. This is just my water. Okay? So C0 versus C5. Transitivity of indifference means that I have to be indifferent between these two. But that's good water. That's salty. I can tell the difference between these two. So the cups of coffee problem lets us know that sensory limitations are a real issue with rationality. So in other words, if you choose a set of alternatives where the things are so close, if your X has a lot of alternatives that are really similar to one another, then rationality on weak preferences, which then leads to transitivity of indifference, might be a real pain, because that just isn't true. Imagine I would have to be indifferent if we just complete this process several times. I would have to be indifferent between that water and this water. Don't try this at home, I told you. You see what I'm saying? The cups of coffee problem. Let me put the salt water away before I drink it. Ugh. I do feel a little sick now. That had better show up in the evaluation forms. Professor really cares about students. Makes this obvious by drinking salt water. Got a fresh can of C0, and I'm looking forward to plowing through it. So that's the fable of the rational binary preference relation. We assume that there's a weak preference relation that captures is at least as good as, and we assume that that relation has 3 properties. It must be reflexive, it must be complete, and it must be transitive. We then define strict preference and indifference with respect to that weak preference relation, and it turns out that there will be downstream substantive consequences, both reasonable and unreasonable, for all 3 of those relations. What are the downsides of this approach? Well, it's a little cumbersome, right? So if I have 2 alternatives, And let's not worry about the reflexive part. Let's just think about alternative to alternative. If I have two alternative, then I have to know data about one pair of them, which is just the two of them. If I have three alternatives, I need data on three pairs. If I have four alternatives, I need data on 1, 2, 3, 4, 5, 6 pairs. If I have five alternatives, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? Yeah, 10 pairs. Actually, what I'll end up needing, if I have n alternatives, 1, 2, 3, 4, 5, however many, I will need n times n minus 1 over 2 pairs to be compared. Right? So in a situation where there are 100 alternatives, if you go into a mini mart, and there's probably 100 different kind of beverages in a mini mart, right? In order for this binary story to make sense about how you go into a mini mart and make choices, you would need to have 9,900 divided by 2. You would need to have 4,950 different pairs to compare. That's a lot, right? It's implausible to think that you, a person in a mini mart, when you make a choice, it need not be the case that you made 5,950 comparisons. And we haven't really talked about what choice looks like in this situation. So we're going to assume that we haven't talked about choice. All we talked about was preference, right? All we've said is what's as good as something else, what's better than something else, what's not as good as something else. Well, what gets chosen? Okay, let me define one quick set. So I'm going to define the set of maximal elements. And that's going to be the set of all little x's and big X, which is to say the set of alternatives, right? So we're choosing some set of alternatives such that x is at least as good as y for all y in x, right? So the set of maximal elements is the set of all alternatives that are at least as good as every other alternative. So if you go into a mini mart and you buy a Coke, implicitly, if I asked you, hey, how do you feel about Coke versus Diet Coke? Coke versus Sprite, Coke versus Pepsi, Coke versus Diet Pepsi, Coke versus Mountain Dew, Coke versus Monster Energy Drink, Coke versus Fiji Water, Coke versus Frappuccino, Coke versus milk, Coke versus apple juice, Coke versus orange juice, Coke versus cider. Hey, how do you feel about Coke versus all those things? You would say, I like Coke at least as much as all of those. Otherwise, I wouldn't have picked it when I had all those other options available to me. Let's assume that price isn't a big thing for you right now. Okay, so like when you bought that Coke, if somebody asked you after how you feel about Coke versus everything else, you would have said it's at least as good as everything else I could have chosen. So these maximal elements, we're going to assume that the choice is going to be something from the set of maximal elements. And then you might be saying to yourself, well, what if there isn't one? What if this is the empty set? That would be a real problem, right? So if you didn't have any maximal elements, then what the heck should we think that you're going to choose if we think that you're rational? Here's good news. With a finite set of alternatives, and with a rational preference relation, with weak preferences that are reflexive, complete, and transitive, the set of maximal elements will never be empty. So you will always have something to choose from. Now, there might be multiple things in there. There might be your 5 favorite drinks. I mean, there are some people that have the same lunch every day. Other people might have the same set of things. Maybe on Monday they go for a burger, on Tuesday they go to a hot dog place, on Wednesday they go to a Chinese restaurant, on Thursday they go Mexican, and on Friday they go Indian. Does that mean that they had inconsistent preferences? Well, no, not necessarily. It just means that their set of maximal elements may have had multiple things. So that's what we assume is getting chosen, but underneath that is a whole lot of comparisons that probably aren't relevant. It's cumbersome. This model, though powerful and intuitive and sensible, and you probably nodded a little bit while you were listening, it's really cumbersome. That's a lot of data to keep track of. We're going to try to find a way to simplify this binary preference relation. We don't want to have to come up with 4,950 comparisons to make just because we want to compare 100 different alternatives. That's annoying. How do we do this in a way that's a little bit more parsimonious? And that's going to be our goal in the B block. Okay, so we just discussed one fable, the fable of the rational binary preference relation. And that fable, it's a plausible story, it's simple, it's easy to tell you. The assumptions of rationality are easy to introduce, they're easy to understand, they're easy to identify problems with. The downside is it's a little bit cumbersome, and it doesn't really tell us that much about what gets chosen. There's a reason that in papers that you've read that may be rationalist, if you read a paper that has rational choice theory in it, if you read a game theoretic paper in international relations or something, you probably didn't see a squiggly greater than or equal to sign. You probably didn't see a binary preference relation like that. Why? It's a pain to work with. No scholar that's trying to make a substantive point that isn't about the nature of preference relations wants to deal with all of that. It's annoying. It's sort of like the Linux. It's the Linux of the three fables. So our three fables are sort of like Windows, Mac, and Linux. And that's the Linux one. It's a real pain to use, but it's a delight if you get it right. So let's try to make things easy now. The second fable that I'm going to show you is the fable that most political scientists use, most scholars working in international relations use when they do rationalist modeling. So this is the most used of the foundational rationality fables, and it's the fable of the utility maximizer. So this theory is going to be based on the same set of alternatives as before. So suppose that we have a set of alternatives, capital X. And the idea here is that we want to come up with a function that carries all of the information from a binary preference relation, but that simplifies just what is involved in that carriage. Oh, that salt is really starting to bother me now. That was a bad idea. And you know what? I did it in my other class too. So I've done that twice now in 2 days. Putting it on top of an iced latte and a chocolate chip cookie may have been a bad idea too. Did I tell you about the bad life choices? Let's just draw a rational preference relation with 4 alternatives. Call them A, B, C, D. A, B, C, D. Okay, so it's reflexive, which means that there have to be arrows from A to A, B to B, D to D, and C to C. And let's suppose, like substantively, let's say that A and B are the best 2 alternatives, and that our decision maker is indifferent between them, and that they like both of them more than C, and they like C more than D. Okay, so if I was going to draw that, I would have an arrow going from A to B, and an arrow going from B to A. That's what indifference looks like. Let's now have an arrow from B to C, and an arrow from A to C. Let's have an arrow from A to D, from B to D, and from C to D. So if I was going to draw this like with a little ranking, I would have A, B at the top, and then C, and then D. And the idea here, so A, B is our set of maximal elements, so we're going to assume that whatever gets chosen will be one of those. And then C is the sort of middle alternative, and then D is the worst. Now look at all these arrows. This is simple. This is 4 alternatives. This is 4 alternatives. The only thing that's complicating this a little bit is the fact that A and B induce indifference. So you could take one arrow away and have a reflexive, complete, and transitive relation, but you couldn't take away more than that. So this is about as simple as you're allowed to get with 4 alternatives. That's really annoying. What we're looking for here is a way to say, give every alternative a number, and then let the ordering of the numbers, let the ranking of the numbers tell you everything that you need to know. If you had to then make a binary comparison, you'd learn what you needed to know from the numbers. So the idea is that we want to assign numbers that preserve that ordinal ranking structure from this complicated picture. We just want to give everything a number. Well, as you may have expected, the way that we would proceed is maybe we'll give D a 1. Okay? And we need C to be ranked ahead of D. Well, that means a bigger number. So let's give C a 2. All right? And then A and B, well, we need them to be as good as each other, but better than C and better than D. Well, let's give each of them a 3. So in other words, A gets a 3, so we'll say maybe f of A equals 3, f of B equals 3, f of C equals 2, and f of D equals 1. And now look, these numbers, the rankings of these numbers, tell you everything you need to know. So then if I said to you, don't look at the picture and tell me how you feel, how the decision maker feels about A versus D. Well, they'd say A has a number of 3, and D has a number of 1. So I think that A must be strictly better than D. And you'd be right. And if I said to you, hey, how does the decision maker feel about B versus A? You'd say, well, B gets a number of 3, and A gets a number of 3, so I'm going to think that they're indifferent. And you'd be right. So this set of numbers, we went from how many arrows are there? Well, if you count the reflexive ones, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 arrows. There's 11 arrows here from 4 alternatives. Now I just have 4 numbers. And those 4 numbers tell me all the arrow stuff I would need to say. So we're going to say, whenever a numeric function like this conveys the ordinal information this way, we're going to say that that function represents the binary preference relation. So let me give you a formal definition of what it is to represent a binary preference relation. And I'm going to officially say that we're talking about a utility function now. So let's define a utility function u colon. I'm saying there's a function named u, and that function reads in x's. It reads in alternatives, okay? And remember, a function is just a rule that reads every dot from one blob to a dot from the other blob. So every x is going to get something, and it's going to get a number. So it's a number that goes from x to the real numbers. So it's a utility function. It reads in alternatives, and it spits out happiness numbers. So, definition. So we say u represents a binary preference relation, squiggly greater than or equal to sign, if x is at least as good as y. So if you have 2 alternatives, x and y, and x is at least as good as y, it has to be the case that every time that happens, if and only if, you would also know that that must be equivalent to u of x being greater than or equal to, in the numbers, u of y. And that's what we just did, right? So we said that if x is at least as good as y in our 4 alternative example, then that means that the number that we gave had to be greater than or equal to the number for the second alternative. So we say that u represents this binary preference relation if there's an equivalence between the rankings of the initial binary preference relation ranking and the numeric ranking that you get from the utility function. This utility function is far simpler to work with, right? It doesn't have n times n minus 1 divided by 2 comparisons to make. It just has n numbers, right? So you're saving a lot. And as the set of alternatives increases, what you're saving is getting bigger. It's getting easier and easier with respect to the binary preference relation fable. This is me just making sure that lecture 1 is working.
We usually view autocracies as countries with polity scores of -7, -8.
I'm so sorry about my voice.
And
I'm really sorry about it.
that are 7, 8, 9.
I'm tired of hearing myself speak already. I'm sure you are too. We have something in common. Okay, so this utility function, the idea is that it carries that information. Now, let me show you something important. So, I'm going to go back to our original 4, where A, B, C, D. A is at least as good as B, B is at least as good as A, B is at least as good as C, C is at least as good as D, B is at least as good as D, A is at least as good as D, A is at least as good as C, and the reflexives. The reflexives is a good band name. It would be like your replacement's cover band to start, but then it would find its own sound. So we've got this simple 4 alternative idea, and we had assigned A, so we said u of A equals 3, u of B equals 3, u of C equals 2, and u of D equals 1, right? And so this does represent the binary preference relation, because every time an alternative is compared against another alternative and gets an arrow, we get what we need on the numeric side. So A is at least as good as A. So we need the utility of A to be greater than or equal to the utility of A. And that's true. 3 is greater than or equal to 3. Likewise with B, C, and D. So we have A is at least as good as B, so we need u of A to be greater than or equal to u of B. Well, 3 is greater than or equal to 3, so we're good. B is at least as good as A. We need u of B to be greater than or equal to u of A, and we have that, so we're good. B versus C, we need u of B to be greater than or equal to u of C. We have that. So likewise with A and C, A and D, B and D, All of them. This is represented. So this utility function represents this preference relation. Now, let's suppose that we decided that A and B were way better or something, right? Well, then let's give U of A, let's call that a Google. And let's call U of B, it's got to be the same, otherwise we won't work because it has to work in both directions with A and B as we've drawn it. So let's give A and B both a Google, and let's give one negative Google. So all that we've done is make these numbers way bigger, right? So we've taken the good numbers and we've made them huge, and we've taken the bad numbers and we've made them huge in the other direction. I sound like a monster truck commercial person. Huge trucks and anti-huge trucks. Cut that. Does that mean that this represents these preferences any differently? No, I mean, it still represents. The utility function has no cardinal information in it. It doesn't tell you anything about intensity of preferences. All that we needed was the ranking to be preserved, and this preserves the ranking just as much as 3-2-1 did. We're not going to lean on that intensity of preference here. So this is an example where a utility function represents a binary preference relation. Let's try a trickier example. So suppose that there were just three alternatives, A, B, and C. And suppose that it's reflexive. Let's keep it reflexive because the reflexives that's our house band. And let's say that A is at least as good as B is at least as good as C, and C is at least as good as A. So let's violate transitivity. So this is complete and reflexive, but not transitive. Now, let's try to build a utility function for this. So A is better than B. So let's give A a 2 and B a 1. Okay, so let's suppose for now that U of A equals 2 and U of B equals 1 because A is strictly better than B. Well, B is strictly better than C, so let's give C a 0. Now C is strictly better than A, but we've already fixed these numbers the way that they are, and we need the A number to be strictly higher than the B number, and we need the B number to be strictly higher than the C number. But we also need the C number to be strictly higher than the A number, and there are no three numbers that'll do that for you. So this preference relation is not representable. We say a preference relation is representable if a utility function exists that can represent it. This preference relation has no such representing utility function. It is not representable, which means that we couldn't simplify this. So if this was a person's preference relations, that's fine. They're not rational because they're not transitive. And we could just model with this. If we wanted to, we could just model with this. We could just proceed, right? This could be our behavioral assumption about how a country's preferences worked. But we wouldn't be able to use a utility function because there is no such utility function that can represent this binary preference relation. So you may now be wondering, well, what kind of preference relations can be represented by utility functions? Which preference relations are well behaved enough that we could simplify them into a utility function, which is way easier to use? Well, guess what? There's a reason that we talked about rationality. So here's your first theorem. We're not going to prove this, but it's not that hard. But here's your first, this is a statement that is true. This is always true. This is a tautology. This is a all the way locked down, drum tight, column of T's in a truth table true statement. And it goes like this. Let X be a finite set of alternatives. So let X be a finite set of alternatives. It could have a Google alternatives in it. It just has to be finite. So let X be a finite set of alternatives. Then a binary preference relation on X, squiggly greater than or equal to sign, is representable by a utility function if and only if it is rational, which is to say it is reflexive, complete, and transitive. So in other words, reflexiveness, completeness, and transitivity are necessary and sufficient conditions for representability by a utility function. So you can think about that in both directions. If you have a preference relation that is reflexive, complete, and transitive, which is to say it is rational, if you have a rational preference relation, then you can represent it by a utility function. And when you see a utility function, you can basically act as if there was some binary preference relation underneath it. You can back out a binary preference relation just by using the numbers. So for example, let's say that I've got three alternatives, A, B, and C. Okay? And I don't know any of the comparisons between them. Okay? Suppose that I only know that u of b equals 3, u of c equals 2, and u of a equals 1. So I'm just starting from a utility function like most papers that use game theory. So I have a utility function. And that's all that I have. It maps alternatives to happiness numbers. So suppose now that I want to draw a binary preference relation picture. I'm going to draw an arrow from one dot to another dot when the utility number from the first dot is at least as high as the utility number for the second dot. So let's think about the arrow from A to A. So u of A is 1 and u of A is 1. 1 is greater than or equal to 1, so I draw an arrow from A to A. Let's think about B versus B. Well, u of B is 3 and u of B is 3. So, and 3 is greater than or equal to 3, so I draw an arrow from B to B. Well, let's think about C versus C. So u of C is 2, and u of C is 2. 2 is greater than or equal to 2, so I draw an arrow from C to C. So I have reflexiveness. Let's think about A versus B. So u of A is 1, and u of B is 3. So 1 is not greater than or equal to 3, so there is no arrow from A to B. 3 is greater than or equal to 1, so there is an arrow from B to A. Let's think about B versus C. So u of B is 3, and u of C is 2. 3 is greater than 2, so there's an arrow from B to C. 2 is not greater than or equal to 3, so there is no arrow from C to B. Finally, let's compare A and C. Well, u of A is 1, and u of C is 2. 1 is not greater than or equal to 2, so there is no arrow from A to C. 2 is greater than or equal to 1, so there is an arrow from C to A. Well, now we have a binary preference relation that is reflexive and is complete. Right? Why is it complete? It's complete because for every pair of alternatives, there's at least one arrow. So now, in order to check for rationality, we need only check transitivity. Well, do we have any chains where one alternative beats another and then the second beats the third? That happens one time in terms of non-reflexive ones. B is at least as good as C, and C is at least as good as A. We need it to be the case that B is at least as good as A, and it is. So in other words, our utility function has created, it is backed out, it is reverse engineered a rational preference relation. Rational preference relation, if and only if, representable by utility function, right? And the set of maximal elements are going to yield the highest utility numbers. So maximal on the preference relation side, choose from among the maximal elements is the same as choose the things that maximize your utility function. So in other words, there's a very deep equivalence between rational binary preference relations and rational maximizing utility functions. That's pretty cool. It means that two fables are equivalent, right? We have identified conditions under which the two fables are equivalent, and those conditions are rational preference relations. So what's wrong with this picture? Well, the utility function, early thinkers in this tradition, like in the 1800s, many believed that there was a real concept of utility. Sometimes it was called, like some fancy French word, ophthalmality or something like that. I can't pronounce it. But they thought that it was a real part of sort of how cognitive processes work in the brain. And they thought that if they learned enough about this, then they would be able to predict choices with scientific regularity. And that's a noble sentiment, but later research has kind of put that aside and said a utility function is just a tool. It's a nice, handy Fable type device that makes it really easy to capture all of the nuances of a binary preference relation, but without having to store all of those oftentimes meaningless comparisons. Utility maximization doesn't actually happen because you don't have, to the best of my knowledge, you don't have a part of your brain that's the utility part of your brain. I'm not a neuroscientist, as you may have noticed. But my understanding is that that isn't how this works. It's not just like you aren't just looking at objects and giving them numbers. You don't do that. I don't do that. Nobody does that. That's some really good C sub zero. Oh, find a picture of Adam Sandler in The Water Boy. Oh, that's some high quality C sub zero. So not only does utility maximization not really happen, to the best of anybody's knowledge anyway. Even if it did happen, it wouldn't be verifiable. Same with binary preference relations. I mean, so you can observe preferences. I don't know that much about what neuroscientists are able to observe these days, and I'm sure that there have been a cajillion amazing breakthroughs that are way over my head. But it would have been national news if they had like found something that they can observe in the brain that tells you how people compare Coke and Diet Coke, and how they compare a cup of coffee with no salt in it and a cup of coffee with 1 grain of salt in it. My rough understanding is that we can't observe that. And we can't observe utility maximization because utility functions are sort of these arbitrary ranking simplifying tools. They're not really a part of us. So neither of the fables that I've told you is a verifiable story. It's not empirically observable, right? These are just ways of saying, here's a way to abstractify what it is to want something. But you don't observe wanting. You observe choosing. So how do we design a theory of rational, which is to say consistent choice? How do we design a theory of consistent choice that is actually about choice? And that's going to be what we do in the C block. So here in the C block, we're going to talk about the fable, the third rationalist fable, the fable of rational choice. Now, here we're going to say, I don't know why people choose the things that they choose. I don't know what's going on in their brain. I don't know what their utilities numbers are. We analysts, we scholars, we observers, we don't observe any of that. And so we're not going to pretend. Instead, we're just going to model choices. Right? So this fable is really hard to work with because we're not going to pretend like we know anything about the decision maker. We're not going to say, suppose the decision maker has preferences, blah, or suppose the decision maker has utility function, blah, right? Instead, we're going to say, I'm going to give this decision maker a bunch of different things to choose from. I'm going to give them a bunch of menus, and I'm going to see what they choose. And then I'm going to check to see if the things that they choose, if their choice patterns are consistent. Okay? So we want a model of consistent choice. We want a model of consistent choice. So then we'll impose criteria on what consistent choices look like that, lo and behold, will actually be about choices. So this is a little bit advanced. You might get a little bit cloudy, and that's okay. This is hard. It's okay. But especially in the international relations context, where like the processes where preferences are formed, you know, where leaders make decisions, or maybe war councils make decisions, or firms make decisions, these are all closely guarded, secretive processes. We have no idea where these preferences come from. All that we can observe when we're empirical international relations scholars are the choices that people make. The choices that the leaders of states make, the choices that the leader of firms make, the choices that happen in international organizations. Many scholars put a lot of time trying to study those mechanisms, and it's a wonderful, important, noble thing for them to do. But it's largely impossible for them to learn about the processes of decision making at the same rate that those decisions are being made, right? So if I'm part of a council that makes a decision, okay, and then you, an analyst, want to come and learn how my council made the decision, it's going to take you some time to learn. You might interview everybody on the council, maybe get some data and analyze it. You have a hypothesis, you test the hypothesis. This is taking a long time. While you're doing that, I've made 10 more decisions. You can't keep up. You can't learn about decision making and the processes of preference formation as fast as I can make choices. So why don't you just learn about the choices? I'm going to be good at this one day, I swear, but right now I'm just awful. This is just awful. Really, really bad. I'm so sorry. But hey, these glasses look cool, right? I think my lighting is a little bit better. So how's this model going to go? Well, we're going to have a set of alternatives, X, the same finite set of alternatives as before. We're going to act like we have a laboratory, okay? So we're an analyst, and we have a laboratory, and we have a decision maker that we'd like to learn about. And this decision maker, we're going to subject to repeated trials. So we're going to say to the decision maker, if I offer you a Coke and a Pepsi, which of these could you imagine choosing sometime? And then we'll give them a Coke, a Pepsi, and a Sprite. And say, which of these could you imagine choosing sometime? And maybe we'll give them just the Pepsi and the Sprite and say, which of these could you imagine choosing sometime? So in other words, we're going to give them a menu, and we're going to be able to do this many times. We're going to give them many menus, but each time we give them a menu, we say to them, hey, which items on this menu could you imagine choosing sometime? And then we're going to check to see what they would choose. So I've got X, a set of alternatives, but that's not enough this time. I need the menus, right? So but every time I give a menu is just a subset of the set of alternatives, right? So if all of the alternatives are A, B, C, D, and E, let's say, Coke, Pepsi, Sprite, Diet Coke, and A and W, right? So if I've got 5 alternatives that I want to learn about choices on, any given menu will be a subset of the set of all alternatives. So if I want to offer somebody an A, a B, or a C, well, that A, B, C, that's just a subset of A, B, C, D, E. So a menu is just a subset of A, B, C, D, E. And so the set of all menus in this simple version of the model is going to be every non-empty subset of X. So now I have a set of sets where each of the component sets is a menu. Let me give you an example. So let's say that I've got 3 alternatives this time, A, B, and C. So if I have 3 alternatives and I need to find every non-empty subset of A, B, C, well, let's think about that. Well, just A by itself is a subset. B by itself is a subset. C by itself is a subset. These aren't very interesting. From a choice standpoint, if I offer you a Coke and say, which of these could you imagine choosing sometime? We're not going to allow you to say none of them, so you would just say Coke. Okay, then we have some binary choice contexts, AB, AC, and BC. And we have sort of the omnibus choice context, ABC. So I've got 7 subsets. I've got 7 non-empty subsets of a 3 alternative set. So I'm making a pretty strong assumption here that we have every non-empty subset of X. Now, it turns out that the number of non-empty subsets of a set with n elements is 2 to the n minus 1. So I had 3 here, and so that's 2 to the 3 is 8, minus 1, that's 7. If I had 4, 15. 5, 31. 6, 63. 7, 127. So in other words, the set of menus, the set of times I have to repeat this trial is getting bigger really fast as the set of things I want to compare is getting bigger. Now you could imagine whittling down the set of available menus, but I don't want to have to talk about all that nuance. Previous experience tells me that in classes like this, that can be confusing. So I just want to say, imagine that we have every non-empty subset. Imagine that we got a huge National Science Foundation grant that allows us to run as many trials as we want. Okay? So in other words, we can get all of these comparisons if we wanted to. Somewhat implausible, but also easy to weaken. Sometimes you see this called a saturated set of menus. Saturated in the sense that every possible choice comparison gets observed. So that's what the set of menus looks like. It's a set of sets. And you're like, can there be a set of sets? There can be a set of sets. So there's 3 elements of this model. 1, the set of alternatives, X. 2, the saturated set of menus, which is just every non-empty subset of X. We need a third thing. 3 is going to be a choice function. It's not really a function, it's a choice mapping, because it's going to, so for any menu, call it C of little m. So this is a function that reads in a menu, it reads in things from the set of all menus, and it spits out subsets of that menu. Okay? So this is allowed to go to multiple dots. It's not really a function. It's more general than a function. So we're going to say that C of M, for any menu M, C of M is not allowed to be empty. So you have to say, I could imagine choosing something, right? Or at the very least, if something isn't in the chosen set, that means that you would like never choose it. It's way worse than anything else in the menu. And so we're going to say that C of M has to be a subset of M. So if I give you 3 alternatives, you can choose one of them, you can choose 2 of them, you can choose all 3 of them, but you can't choose none of them. Likewise, if I give you 4 alternatives to choose from, if your menu has 4 items on it, you can choose 1, 2, 3, or 4. Like if you're indifferent between them, if you're indifferent between all 4 alternatives, then just say they're all fine. Okay? But if you hate one of them, then you say, well, don't give me the first one, but I'll take 2, 3, and 4. Something like that. Okay, so this choice mapping reads in a menu, and it says, okay, I'll take something off of the menu. I'll take the menu. I'll take something from the menu, and maybe I'll take the whole menu. That's how my dad orders appetizers at restaurants. He's just like, I can't tell which appetizer I want. Just bring me one of every appetizer. We call that the bill. My dad's name is Bill. My mom's signature move is to eat all the appetizers. We love food, we're Italian. So I've got this choice mapping, and I need to come up with a way to say what is a consistent choice, and I don't know how you're making these choices. So in these trials that we're running, if I offer you Coke, Pepsi, and Sprite, or war, peace, or nuclear war, or sanction, tariff, nothing, right? Or if I offer you any set of options, and I see what you picked, or I see what you rejected, sort of implicitly, I don't get to ask you why. I'm not trying to learn about your preferences. I'm not trying to learn about your utility. I'm just trying to observe your choices. So the question becomes, what is a consistency criterion in this framework, in this fable? Okay? The name of that criterion, it's called the weak axiom of revealed preference. Weak axiom of revealed preference, or warp. W-A-R-P, warp. This is part of revealed preference theory as developed by Paul Samuelson in the early and middle 20th century. And the idea goes like this. If I observe, the analyst, okay? If there's a menu, M we'll call it, that's the first menu that we observe. And let's say that in M, there are 2 alternatives, maybe X and Y. So if we observe a menu called M, and 2 alternatives in it called X and Y, and we see that X is an element of C of M. Okay, so let's think about what that looks like. We had a menu. It could have a lot of things on it, it could have 2 things on it, but regardless, the one thing that we know about this menu is that X and Y are on the menu. Okay? And we observe that X is among the things that get chosen off of that menu, M. Okay? So we see this. We lock that in. Okay. Now the question is, what sort of consistency requirement would be reasonable, right? What sort of other choice, what sort of other menu, and then choice on that other menu should we be able to rule out, right? So you might even want to pause the video. Think about answering this question. If you observed this situation, a menu that had X and Y in it, and X among the things chosen. Maybe Y was chosen, maybe Y wasn't. Okay? Then what should you be able to rule out for some other menu? Here's a hint. That other menu that you should be able to rule something out on probably has X and Y in it. Pausing the movie again. Okay. Here's the answer. So if you observe that menu that has X and Y in it, and X was among the things chosen, maybe Y was, maybe Y wasn't, then it can't be the case. There cannot exist some other menu M prime. So there cannot exist some other menu M prime that has X and Y in it. Right? So there can't be some other menu where X and Y are both on the menu. Y got chosen, off of menu M prime, and X didn't. So here's the idea. In menu M world, in the first part of our implication, right, there was a menu, and that menu had X and Y on it, and X was one of the things that you chose, which means that you revealed a preference, we're thinking here. This is what we're trying to say. You revealed that X was at least as good as Y, is what we're saying. So you reveal, through your choices, that there's a world out there called M, where X and Y are available alternatives, and X was one of the things that wasn't so awful that you chose it. Okay? Then what that rules out is there can't be some other world, the world called M prime, where X and Y are available alternatives. Y gets chosen and X doesn't. You revealed to me that X was at least as good as Y. You can't then reveal to me that Y is strictly better than X. So what the weak axiom of revealed preference does is it says your choices have to be consistent. And if you show that one alternative is at least as good as another in your choices, then you can't in some other choice context say, well, but this time Y is strictly better than X. So that's our consistency requirement. There are a couple of flavors of warp. It's one of those funny things. So Paul Samuelson was not known for his humility, and he was a very direct writer. So you always knew what he was saying when he wrote. And so when he defined warp the first time, he said, and he didn't define it formally, he defined it sort of in words. And he was a big proponent of mathematics and the social sciences. This was just him thinking that something was clear. And that's what happens. That's why we need to do this, is because sometimes things aren't clear. And so he wrote something to the effect of, well, this is a perfectly clear definition, and I suspect that it's going to be rapidly accepted by all people in the social sciences. Like I said, he wasn't known for his humility. Which is fine. He didn't need to be humble. He was awesome. The funny thing is, after he had that plain language description of warp, then like 4 different formal alternatives. So there's different flavors. This is the easiest one, if you ask me, and it's the most relevant for what I'm about to show you. But it's good to have precise formal definitions for exactly that reason. So this version of warp has a very nice result. So let's say, much like before, that we could back out a preference relation by observing choices, okay? So I'm gonna say X squiggly greater than or equal to with a star to show you that it isn't real. It's sort of something that we observed. We're making this up. We're reverse engineering a preference relation. So I'm gonna write X squiggly greater than or equal to star Y. And that's gonna be my way of saying there was a time where X was revealed to be at least as good as Y. And I'm gonna write that if and only if there exists a menu such that X and Y are in the menu, and X is one of the things chosen. X is revealed to be at least as good as Y if and only if there exists some menu where X and Y are both on the menu and X was one of the things chosen. So here's an interesting truism. Actually, it's more than just a truism, it's a theorem. And the theorem goes like this. Let X be a finite set of alternatives, and let capital M be a saturated set of menus, which is to say, the set of all non-empty subsets of X. So we're going to be able to look at every single choice context. Again, we can weaken that. And if you ask a question about that during the meetings, I'll be happy to expound on that a little bit, but I think this is good for our current purposes. So let X be a finite set of alternatives, and let M be a saturated set of menus on X, which is to say every non-empty subset of X. Let C be a choice mapping, which is to say a rule that reads in a menu and spits out a non-empty subset of that menu. Okay? So it reads in a menu and it spits out a non-empty subset of the menu. So that's our context. That's the model that we've described. Set of alternatives, a set of menus, and a choice mapping. And here's the truism, and it's going to work. It's going to be an if and only if. The choice mapping satisfies the weak axiom of revealed preference. So the choice mapping satisfies warp if and only if its revealed preference relation is reflexive, complete, and transitive. So in other words, warp, if and only if, rational. And we had utility representability, if and only if rational, which is to say all three of our fables are equivalent. Let me say that again. I told you three fables today. The fable of the rational binary preference relation, the fable of the rational utility function, and the fable of the rational choice. And under appropriate definitions and certain scope conditions, those three fables are the same. If you know about one, you know about the other two. If I write down a utility function, it's true, it's super easy, it's super convenient, it's super laughable on a substantive level. But if I wanted to justify it to somebody, I would say something to the effect of, well, if you don't like utility functions, we could try a binary preference relation thing, and chances are good you don't like that either. Or we could try a warp satisfying choice relation, which is far more general, actually. And then usually, if somebody doesn't like utility functions, they don't like either of those two things either, but it's nice to try to keep somebody happy. And note also that we still haven't talked enough about the mechanisms here, right? So we're not political psychologists. You can imagine why these models have been the target of lots of good psychological theorizing. That's going to be a recurring theme. The psychologists, or the behavioral political scientists, that see stuff like this oftentimes are nonplussed with the lack of mechanisms for understandable reasons. So if you're somebody that's interested in how that mechanism would play out, I would encourage you to go take either a decision theory class or in a psychology department. I know that we have some classes in that. Or take some psych classes or political behavior classes. We're so lucky to have a political science department so full of amazing behavioral scholars that could teach you exactly what things are wrong with these models. I would be, and I'm always happy to hear their criticisms, and I learn a lot from them. But I'm not convinced. I think this is a pretty useful set of fables. And that's okay, we're allowed to disagree. Reasonable people can disagree. So just to rehash what's happened over the last blah hours, right? We talked about rationality from three different mathematical angles. We talked about it from a binary preference relation angle. We talked about it from a functional, like a utility function angle. And we talked about it from a choice theoretic angle. And it turns out that under appropriate definitions and appropriate scope conditions, those three fables are equivalent to one another. For the next 2 weeks, we'll talk a little bit about preference relations, but then it'll all be gone and it'll all be utility functions, which are laughable substantively, but which can then back out interesting substantive stories, be they preference relation or choice theoretic. So I want to conclude with a provocative thought that also gives a preview of coming attractions for next week. So at the beginning of today's lecture, which feels like it was yesterday, I said that there's no one reasonable way to look at a given set of alternatives. Rationality has nothing to do with reasonableness. It only has to do with consistency. And so you could imagine a society full of consistent people that still disagree very often. They have rational preference relations, maybe. They have preference relations baked inside of them that are reflexive, complete, and transitive. But that doesn't mean that they have to agree with one another. They can have heterogeneous preferences. If you go to the movies, and I go to the movies, and we're picking a movie together, it doesn't have to be the case that even though we both have rational preferences over the movies, that doesn't mean that we have to have the same preferences over the movies. So, the next question is going to be, well, if we're picking movies together, how do we come up with some societal preference ranking, right? How do we take these heterogeneous but consistent preferences and then turn them into a decision that stands in for all society? So if we're going to model countries as if they were people with utility functions, which is to say as if they were people with rational preferences because of that equivalence we talked about today, well then what's the rule that reads in a society of individuals and spits out a ranking? And that's going to be what we talk about next week. But provocatively, I want to ask, is international relations of a rationalist flavor doomed from the start because these decision-making processes that we know that we're not getting a good enough picture of on the individual level, does that crappiness on the mechanism side, does it get worse as we aggregate? I don't know. I really don't know. But it's an interesting thing to think about. The fact that our theories are incomplete in terms of how individuals make choices, are those little gaps, are the unanswered questions, when we take them and then we add them all together, one for every person in society. So there are unanswered questions about how I make decisions, there are unanswered questions about how you make decisions, there are so many unanswered questions. So remarkably, we're still going to proceed as if we can aggregate preferences at a societal level. Does that mean that this is stupid? I don't think so, but I could be wrong. And so this is what I want you to have on your mind when we think about strategic international relations, which is to say rationalist international relations, which is to say imagining processes between groups. We can't have a system of international relations that is entirely individualistic. But the models of individual decision-making are themselves flawed. Do those flaws have to go somewhere bad? Think about it. In the meantime, I hope you enjoy this week's problem set, and I can't wait to see you on Monday. Thanks for watching.